Next we will talk about discretization methods, starting with the pressure gradient term in the momentum equation. Discretization refers to the method used to interpolate solution variables from the cell centroids, where they're calculated, to the cell faces, where values are needed in order to compute fluxes and gradients. For the pressure gradient term, what happens is we use the Green-Gauss theorem to calculate the pressure gradient. This theorem says that the volume integral of the gradient of a scalar is equal to the surface integral of the scalar over the bounding surface of the volume. So for a cell in a CFD mesh, it can be written the way that it appears here on the slide. The result of this, though, is that while the pressure on each cell face is required in order to compute this term, the pressure itself is only calculated at the cell centroids, so we need a way to interpolate from the cells to the faces. The schemes that are available in Fluent for doing this are listed here. The default scheme is called standard. This scheme should not be used where there's flows with large surface normal gradients near boundaries, which is common in natural convection problems. In problems like this, it's better to use Presto instead. The Presto scheme, in addition, can be used for highly swirling flows, flows involving steep pressure gradients like you would encounter with a porous media or a fan model, and also in strongly curved domains. The linear scheme can be used if the other options result in convergence difficulties or unphysical behavior. But linear is very inaccurate, and if you find it's the only scheme that's allowing the solution to converge, it could mean that there's something else very wrong with your grid or problem setup. The second order scheme can be used for compressible flows, and it should be avoided for porous media, for any kind of jump boundary, fan boundary, or multi-phase models involving the volume of fluid or the mixture model. And the final scheme is body force weighted scheme, and this can be used where you have problems with large body forces such as high Rayleigh number natural convection or highly swirling flows. Similar to pressure, when we have a convective term in an equation that we're solving, we need to interpolate values from the cell centroids to the faces of the cells in order to compute the convective flux into the cell. The schemes available to do this are the first order upwind scheme, which is the easiest scheme to converge, but it's only first order accurate. The power law scheme, which is more accurate than the first order scheme for flows where you have very low Reynolds numbers. The second order scheme, which uses larger stencils for second order accuracy, and we'll explain more about that later. This scheme is essential to use if you have triangular or tetrahedral mesh, or any time that the flow is not aligned with the grid. It's more accurate, but it may result in slower convergence for the solution. The monotone upstream centered schemes for conservation laws, which are more easily referred to as muscle. This scheme is locally third order discretization for convective terms on unstructured meshes, and it can be more accurate than second order schemes for predicting secondary flows, vortices, forces, and so on. The quadratic upwind interpolation, or QUIC scheme, applies to quadrilateral and hexahedral cells or to hybrid meshes, and it can be useful for rotating and swirling flows, and if you have a uniform quad or hex mesh, is formally third order accurate. In practical terms, the effect of higher order discretization is that the numerical solution is less diffusive, and that's what we illustrate on this slide. Remember, the situation is like we were just talking about, where the solution is being computed at cell centroids, but the computation of convective fluxes requires solution variables at the face. In this illustration, if we say that the flow at face F is going from cell C0 towards cell C1, then the value at the face is calculated with the equation that we have here, where the face value is equal to the value of the upstream cell, C0, plus a contribution from the gradient at the cell centroid in the direction of the cell to face vector, and then multiplied by a factor beta. First, imagine that beta is equal to 0. In this case, then, the face value is equal to the value of the upstream cell, and this is what happens in the first order upwind discretization scheme. This scheme is robust, but it is only first order accurate, and so it's mainly useful for initial runs Next, imagine that beta is 1. Now this kind of looks like we're using a Taylor series expansion to estimate phi sub f, and this is what happens in the second order upwind scheme. Some additional measures are taken to ensure that the solution remains bounded, which means that the face value should be in between the value of the cells on either side of the face. And finally, if you choose a quick discretization scheme, it effectively maximizes beta throughout the flow domain while keeping the solution bounded. The effect of the discretization scheme is most dramatic when the flow is not aligned with the grid, as we see in the example on the right of the slide. What we have is there's an inviscid flow that's going from lower left to upper right. There's a scalar which has a value of 1 at the left-hand boundary and a value of 0 at the bottom boundary. And you can see that because there's no diffusion in an inviscid flow, that the theoretical solution is shown here where there's a distinct boundary between the two scalar values. In the solution calculated using the first order upwind scheme, there's a wide region of diffusion between the two streams. This is an inviscid flow, and so that means that the diffusion we see here is purely numerical diffusion resulting from discretization error. With both the second order upwind schemes or the quick schemes, as you see here in the lower corner, the effect of the numerical diffusion is much less pronounced than it is for the first order upwind scheme. We've seen the way pressure is discretized and also convective fluxes are discretized. When Fluent solves an equation that includes a diffusive term, the discretization scheme used for this term is always a second order accurate central differencing scheme. The final bit of numerics that we want to talk about is how gradients are calculated for use in higher order convective terms and also for diffusive fluxes. There's 3 choices available in the solution methods panel. The idea with Green-Gauss cell-based gradients is that for a given cell, the value on each face is averaged from the neighboring cells, and then once the face value is there, then the gradient is calculated in a manner similar to what we saw a couple of slides ago for the pressure gradient. This is good, but the solution can have false diffusion and smearing of the solution fields. Green-Gauss node-based gradients also use the Green-Gauss theorem, but here what happens is the values at each node of the cell are taken from a weighted average of the surrounding cells, and then those node values are averaged to obtain the face values before the Green-Gauss theorem is applied. This is a more accurate method than the cell-based method because, as you can see here, a larger group of cells, or a wider stencil, is used to compute the gradient. So this helps to minimize false diffusion, and this scheme is strongly recommended for triangular and tetrahedral meshes and for hybrid meshes. The default method is the least squares cell-based method. This method also uses only the values from the neighboring cells, but the least squares method, when using only the cell values, is more accurate than the Green-Gauss cell-based method because it can exactly reconstruct the linear field on highly skewed or distorted meshes. The least squares cell-based and Green-Gauss node-based methods have comparable accuracy, but the least squares method is slightly less computationally expensive than the node-based method. So for this reason, that's why it's the default method, and this is appropriate for any kind of meshes.